This new section is entitled the power theorem. The first theorem that we're going to prove is, once again, using a circle. If you have a chord AB and you have another chord CD and they intersect at point E. So each chord now has two pieces. For example, AB, you can say it's AE combined with EB. CE with ED. And the theorem says that if you take one chord, say AE, and you multiply the two pieces, AE and EB, and you take the other chord, CD, you multiply it by the two parts that make it up now, CE and ED, equality you get. And of course, we need to prove this. It's no fun not to prove it. So let's draw it a little bit bigger. You have AB, CD, and point E. Now, let us draw AC, and let us draw BD. Now, of course, this angle and that angle, let me call it number 1, excuse me, they're equal. So we now have two triangles, and these opposite angles are equal. They're both angle 1. Alright, now let's look at angle C for a moment. Let's look at this angle. One end of it is at A, the other end is at D. It cut off arc AD. But angle B did the same thing. One end of angle B is A, the other end is D. It cut off the same arc. That makes those two angles equal. Angle C and B are the same. Well, we can use the no choice theorem if you have two triangles that have two corresponding angles. The third ones must be corresponding. That is, angle A and angle D are congruent. Well, of course they are. They both cut off arc CB. Okay, so now these two triangles, triangle 1 and triangle 2, are similar. And we're done at this point. If you take AE from triangle 1, AE is made up between the angle with 2 slashes and the angle that we called 1. But that's exactly ED in triangle 2. ED is made up from angle 1 and the one with 2 slashes. And that ratio should be the same as the division of any other two congruent sides in these triangles. Like CE is in triangle 1, the top is triangle 1, the bottom is from triangle 2. CE, well, it's one end of CE is angle 1, the other end is the angle with 1 slash. But that's exactly BE. One end is 1 slash, the other end is angle 1. EB. And something I hate to say, but in this problem I will, is you cross multiply. That product, AE times EB, must be equal to CE times ED. Or you can reverse that. So we got exactly what we said. Again, if you have two chords that cut one another, one chord is made up of those two pieces. If you multiply those two lengths, and this chord is made up of those two pieces, and if you multiply those two lengths, those products will be the same. That's what this theorem is saying. This is the secant-secant theorem. Or, sorry, chord-chord theorem. But what if you have a tangent to a chord? What if you have a tangent to a chord? What if you have, at this point, a tangent line, and then you have a chord? Like always, we call this point P. P for point. And you have A, B, and C. Well, it turns out that the theorem states that the length of the chord squared is going to equal to the long line PB times the exterior PC. That is from B to P and then from C to P. Everything to the point. Okay, now why is this true? Well, what I would do is I would make one big triangle, BAP, and another triangle, ACP. Now, notice that this angle cut off this arc, and so did angle B cut off that arc. So, angle A and angle B equal. And clearly, angle P is in both of the triangles. Again, we're talking about triangle ABP. And I want to show that it's similar to triangle ACP. Okay, so now what we've shown is that we have two pair of congruent angles, in these two triangles. Well, that means the third angle is equal. In this triangle, that's the third angle. In this triangle, use a different color, it's this big angle A. That's the same. Okay, we have two triangles that are the same. I'm going to take PA from the big triangle. And that, the easier way is to call angle P with 3 slashes. So I've already, that third angle that I said by the no choice theorem should be equal, the green and the one by angle C, I put 2 slashes. So I changed angle P. So in the big triangle, PA is between 2 slashes and 3. In the smaller triangle, that's CP or PC. 2 slashes, 3 slashes. Okay, big to small. In the big triangle, we have PB. This long one. It's between 1 slash and angle P with 3 slashes. While in the little triangle, you have 1 slash and angle P. Well, that's AP or PA. And if you cross multiply, PA times PA is PA squared, and you cross multiply on the other side, you get PB times PC. Exactly what we set out to show. Exactly what we set out to show. Okay. I'm going to erase this, do something else. Now, let's do, so we just did secant or tangent to tangent secant. Let us do a exterior point. Let's do secant secant. If this is A, B, C, and D, this theorem is straightforward. Always deal with P. AP times BP is equal to CP times DP. The long one to the short one. Now, thing is two short ones. We could have said that short one. That's why I say it's always to P. It's A to P times B to P. That equals C to P times D to P. Everything is to P. Let me draw this again. A, B, C, D, P. Now, somehow we need to prove that these are equal, that this theorem holds some order. Well, I do this, and I do that. And then I say, oh, A, oops, I don't know what happened here, but that's a D. A, B, C, D is a four-sided polygon. It's a quadrilateral inscribed in my circle. That is angle 1, and I'll call this angle 2, are supplementary. That is 2 plus angle 1 gives me 180. So then that's angle 1, because this big angle is 180. And what you add the 2 to get to 180 is angle 1. Same argument here. If I call this angles 3, well then this also has to be angles 3, because they're both supplementary to angle 4. You can't have two different supplements. Okay. Basically, I don't really need 2 and 4 in this problem. They just helped me argue why those two angle 1s are equal and those two angle 2s are equal. So now I have two triangles. I have APC, the big one, and I want to show that it's similar to the little one, which is BPD. Well, they have the same three angles. This triangle and this triangle have angle P, and they both have an angle A and D are equal, and B and C are equal. These are congruent triangles. They really are. AP. One end is angle 1, the other angle is angle 2. That's the big triangle, big to small. In the small triangle, angle 1, angle P, that's DP. That's DP equals. Now I'm going to use another ratio. Top better be the big, bottom better be the small. You want to put the smalls on the top and the bigs on the bottom, fine. But you have to be consistent. In the big, we have AP by BP. Well, it's actually easy. CP. Yeah, CP, excuse me. That's the big one. It's between angles 3 and, of course, angle P. Well, that's BP in the little triangle. Angle 3, the right angle. Cross multiply gives me AP times BP. This product is equal to that product. CP by DP. So, yep, it really, 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 really is true. Okay, you need to be able to prove these theorems. The more you accept without really being able to prove it, the less good you are at math. Okay. So, we'll do a handful of problems and then we'll be done. Like always. The first one is as follows. You have a circle, you have two chords. This chord is 3, this chord is 8, this is 2, this is x. Find x. Well, this chord was broken up into two pieces. One is 3, the other is 8. Equals the other chord, this long chord, is broken up into two pieces. One is 2, the other is x. Now there's two ways of doing this. 8 is 4 times 2. 2 times this. 2 times 12 is 2 times 12. X is 12. Or if you preferred, divide both sides by 2. Divide the right side by 2, just get x. Divide the left side by 2, get 3 times 4, or 12. So we found 12. Suppose we have a tangent and a chord. Well, actually, let's do that one next. Chord. X, 3, 5, and 10. That's 5, that's 10, that's x, and that's 3. So there's P. It's from here to P, which is x plus 3, times from here to P, which is 3, equals this point to P, which is 15, times this point to P, which is 5. So x plus 3 times 3 is 75. That's 25. 25 times 3 is 75. X plus 3 is 25. That's 22. 22 plus 3 is 25. And if I didn't say it, the instructions is defined x. Now, I'm not saying you don't know 25 times 3 is 75. But what if the numbers were less friendly? Maybe the 75 was lots bigger. You should think of the 15 as 3 times 5 times another 5. This is 3 times 25. If you prefer, 25 times 3. Something times 3 is 25 times 3. This must be 25. What times 3 is 25 times 3? You're given the answer. 25. So x plus 3 is 25. 22 plus 3 is 25. What plus 3 is 25? 22. So x is 22 in this problem. Nice problem. Notice theorems. These are friendly, nice, simple problems. Suppose you have a circle and you have these two chords, A, B, C, D, and E. And I tell you that AC is 10, B is the midpoint of AC, and I tell you BD is 5. And I ask you to find BE. What is BE equal? Okay, well, AC is 10. This whole line is 10. But B is the midpoint. That is, each piece is 5. And I tell you that BD is also 5. BD is also 5. Yeah. But I just make AC 20. And B cut it in half. 10 and 10. And maybe I even ask you to find how long is DE. That's a better one. Okay. Well, first, let's find out what BE is. Call it X. DE was broken up into two parts, 5 and X. So you multiply those two, equals. AC was broken up into two parts. They are each 10. 10 times 10. So 5x is 100. 5 times 20 is 100. X is 20. But DE is DB, which is 5, plus BE, which we just found out is 20. So DB is 5, and BE is 20. So it is 25. Fine. Okay. Try a couple more. So the very routine problems, you need to know which two to multiply. You multiply 2 together, you multiply another 2 together, you put two horizontal lines in between them. So here's our tangent secant. P, Q, R, and S. They tell you that PR is 10. And I tell you QP is, say, 5. And I can ask you two things. Well, what is QS equal? And what is PS equal? So PR is 10. And QP is 5. That's 5. So this here is unknown. Let's call it X. So we always go to P. From S to P. Well, it's X and then 5 more. It's x plus 5. And you multiply it by q to p, which is 5. And that's going to equal, now let's do the top part. Oh, this is tangent. Basically, the long and the short are both 10. So, it's 10 times 10. Now, which is 100. Some of you may not know what times 5 is 100. You really should know how many nickels there are in 100. So, one way of doing it is to break off for 5 from the 10. 5 times 2 is 10, times the other 10. Well, this is 20. 5 times 20 is 100. 5 times 20. X plus 5 must be 20. Well, 15 plus 5 is 20. So x is 5. Well, what does x represent? That's SQ. QS is 5. Now, how long is PS? Well, it's 5 plus 5. It's 10. X is 15, like I said, excuse me. So QS is 15, and then SP will be 15 plus 5, or 20. And you can check, so the whole thing is 20. The long times the outside short, 20 times 5 is 100, and tangent is 10 by 10, which is 100. They are, in fact, equal. Let us try one more. P, Q, R, and S. Tangent at S. PS is 3. How about QR is 8? QR is 8, and we want to find PQ. How much is PQ? Well, for right now, we'll call it X. PQ is X. PS is 3. That's 3. And QR is 8. Well, from it's R to P times Q to P. And this is going to equal to SP squared. Well, RP, R to Q is 8, and then X more. It's 8 plus X. And QP, that's given. That's X. And this is supposed to equal SP or PS squared. 3 squared or 9. Rather than using a quadratic formula or factoring by grouping or completing the square, this is some number, and this is 8 more than the number. And it's supposed to add up to 9. Well, 1 times 9. That's 8 more. And 1 times 9 is 9. I know what X is. X is 1. X is 1. PQ is 1. You don't have to use the quadratic formula. But just for the record, mathematically speaking, if you just have this equation, x equals 1 is not the only answer. Because if you switch these two numbers and change their signs, -1, -9. If x is -9, well, x is -9. 8 plus -9 is -1. And when you multiply those two numbers, so this number is 8 more than this number, and they multiply out to 9. There are my two answers. And I didn't factor, I didn't bring the 9, I didn't distribute, I didn't bring the 9 to the other side, I didn't factor. Just ask myself, what two numbers multiply out to 9 where one is 8 more than the other? Okay, that completes this section.